So good morning, everyone. So today we'll start with the cutting temperature, right? Just give me a minute. So in the cutting temperature, we were discussing that uh, the cutting temperature is generated primarily at the three locations. One is the primary deformation zone or the shear zone. Second is our chip tool interface, that is the secondary zone, and third one is the at the wear out flanks. Okay, so these are the places where the cutting temperature is generated. We were discussing previously, and now I'll quickly share the details with you, share the screen with you, so that you can see the slide. so So we were at this slide in the last class, and I'll continue from here. So the role of variation of the machining parameters on cutting temperature. The magnitude of the cutting temperature is more or less governed or influenced by the machining parameters like work material. As I told you, the work material, tool material, cutting tool geometry, cutting parameters or process parameters like cutting velocity, feed, depth of cut, the cutting fluid. All these things are essential, or we can say means factors which can control the cutting temperature, right? Okay, so what I'll do is I see there is some kind of noise coming from the background. So uh, I'll, as of now, mute everyone. Okay, and during the question answer session, I can unmute you and you can. So again, I'll be sharing the screen with you. That is where we were. so, so these are the factors on which the cutting temperature depends on. Then the control of the cutting temperature. So we have seen that if the cutting temperature is high, it is detrimental to both the tool and the workpiece. So the cutting temperature is required to be controlled, and we can control the cutting temperature by proper selection of the material and geometry of the cutting tool. Now suppose we are using some material as a workpiece which is very hard, and we are not using a proper tool for cutting that hard material. Like we know that the cutting tool should be harder than the work material. So that we have not considered here. So what will happen is the cutting temperature will generate because there will be rubbing action and no cutting will take place, right? So since a material is very hard, it will restrict, or it will try to prevent indentation caused by the cutting tool, right? So rubbing action will take place and there will be no cutting. However, temperature will keep on rising. So that is not really desirable. So proper selection of material and geometry of the cutting tool is again very important. Now, geometry of the cutting tool. Suppose you are using a geometry wherein you have a negative rake angle, right? So in that case, again, the rubbing of the chip with the rake surface will be there. So negative rake angle generally is used for tool materials like which are brittle in nature, like ceramic materials. So that has to be considered. And again, optimum selection of VC. This is the cutting speed, and S naught. S naught is your feed, cutting speed and feed combination without sacrificing the material removal rate. Proper selection and application of the cutting fluid, the application of special technique if required and feasible. Like in few cases some special techniques are used, as in you can say some softening of material before the machining is done. Like special technique, there is a process where hot machining, which we has already been discussed previously, that in case of machining hard materials, what we do, we heat, use the cutting temperature for heating up the material, and the material softens, and then it becomes easy for machining. Right. So these are the special techniques. There are many other special techniques like this that can be used in order to reduce the cutting temperature at the cutting zone. Now, when you're heating the workpiece, that is not the cutting temperature. We can use some other flame or maybe some laser source to heat the workpiece, right? So that will definitely not increase the temperature at the cutting zone, right? We can use some other cutting fluid, or we can use some uh, MQL technique, right? Minimum quality quantity lubrication technique, wherein we can also use some cryogenic material, like liquid nitrogen, liquid oxygen can be used. So different types of special techniques can be used, right? There are many of them. Now the basic methods of controlling the cutting temperature is that, particularly when the temperature is very high, we have seen that it is not very good, or it creates it happens, there are situations where the cutting tool and the job are prone to damages. So we need to control this cutting temperature, and we also have to make sure that the productivity and the quality of the product is not getting sacrificed, right? So we have to use the proper cutting tools, the materials of the tools and the geometry should be proper. The cutting velocity and feed should be selected properly, and we also need to select the application procedure of the cutting fluid. Now, for the reducing the cutting temperature and the effects, detrimental effects of the cutting temperature, we have to select the material and geometry of the cutting tool. So as we have already discussed that this plays a significant role. So suppose physical vapor deposition or chemical vapor deposition coating on the HSS, okay, high speed steel and carbide tool, enables reducing the cutting temperature by reducing the friction at the chip tool interfaces. Okay. Now, in high speed machining process of steel, lesser heat, and as we have already seen that in the cutting speed is very high, the heat generation is also very high. However, if the feed is high, the uh, temperature generation is less. So we have to select the optimum cutting speed as well as the optimum feed, so that we can reduce the cutting temperature. So in case of high speed machining of steels, lesser heat and cutting temperature develop if machined by cubic boron nitride tools, right? So normally high speed machining will generate more temperature, but in case you are using the cubic boron nitride tools, that will generate lesser temperature than the HSS or any other metal tools. Okay, so these cubic boron nitride tools produce lesser cutting force by retaining its sharp geometry, because it's very hard, and definitely the hardness is a factor wherein the tool wear becomes less, so it retains its sharp geometry, and also it is very stable chemically. So there is no kind of chemical dissolution of that tool, uh, or any kind of built-up formation that takes place and in the normal HSS tools. That does not happen in case of cubic boron nitride tools. The cutting tool temperature of the ceramic tool decreases further if the thermal conductivity of such tools is enhanced by adding some thermally conductive material. Okay, so if I add any kind of thermally conductive material with this ceramic tools, because ceramics we know that they are non-conductive in nature, So dissipation of the heat will not be possible properly. So what we do is we add some aluminum oxide or any kind of carbides, we can say, so that the heat can be extracted out and the cutting zone can be the cutting temperature at the cutting zone can be lowered down. So cutting temperature can be sizably controlled by also proper selection of the tool geometry in the following ways. Large positive tool rake helps in reducing the heat and temperature generation by reducing the cutting forces, but too much increase in the rake mechanically and thermally weakens the cutting edges. Right. So again, you know that if you see, I'll just quickly draw the rake angle. So this one, this is the rake angle, right? Okay, let me select a smaller size. Okay, this one is your rake angle, gamma. Now this, if this rake angle is increased, that means this cross section decreases. So this cross section of the tool decreases and it may break when it is when the cutting forces are higher, right? So that is also not preferable to reduce the rake, because we know if you to increase the rake angle. So this is the positive rake angle, this is the positive rake angle. Now if you go above the pi r plane, then it will be a negative rake angle. So rake angle, we know it's provided so that we can have smooth removal of chips and the chips do not rub with the rake. So definitely, again, very less amount of or very small rake angle is not again desirable, right? So we have to select the optimum rake, right? So that is what it says, that too much increase in the rake mechanically and thermally weakens the cutting edges. Again, compound rake preferably with the chip breaker. Now, chip breaker, I told you once that chip breakers are used for removal of, in case of ductile material cutting, wherein continuous chips are formed. So there is a chance of entanglement of the chips with the tool. So that is preferably it's not preferred, like because the machining zone get hindered and the chips which are coming out from the workpiece gets entangled with the tool and the workpiece. So that is not really desirable. So chip breakers are they are provided so that it can remove the chips, it can break the chips and remove the chips from the cutting zone, and this enables reduce in heat and temperature through reduction in the cutting forces. Okay, now and also the friction is friction between the chip and the tool or rake surface of the tool is also prevented. Again, for the same amount of heat generation, cutting temperature, the cutting temperature decreases with a decrease in the principal cutting edge angle. So the principal cutting edge angle, if you decrease, then again the friction will be reduced and the cutting temperature will be reduced, right? As you can see from this equation. Nose radiusing of single point cutting tool not only improves the surface finish, but also helps in reducing the cutting temperature to some extent. We have also discussed once, I'll quickly reiterate that here, that suppose we have this portion of, this is your tool, and this tool is moving in this direction, right, relative to the workpiece. And if you consider the next position of the tool here, That means this much material, this is your surface roughness. This is your surface roughness. Okay. And now if I again draw the same tool with a increased nose radius, please bear with me. I'm just using my mouse to draw this. So, so see, you can see that this reduces. Okay, so I can also draw it here. So increase in the nose radius reduces the uh, surface roughness. So surface roughness and also the cutting temperature is reduced in case we consider the nose radius, and definitely again more if you increase the nose radius more, then it will be a flattened surface and the material will not be removed. Again, optimum value of the nose radius should be selected, so that has to be considered. So anything which you are doing, you should consider the optimum value. Next is the selection of the cutting velocity and the feed. So the cutting velocity and the feed is a very important factor. Cutting temperature can also be controlled to some extent, even without sacrificing the material removal rate, right? So by proper and optimum selection of the cutting velocity and feed with their feasible ranges, the rate of generation of heat and the cutting temperature of generation of the heat which is generated at the cutting zone and the rise in the cutting temperature, that is directly means proportional, or we can say directly related to the amount of power which is consumed, right? Because more cutting temperature is generated, it is due to the cutting, more cutting force is required to remove the material, so definitely more power will be consumed. So here we have a relation here. So power consumption is the pz force, the main force into the cutting velocity, that we can pz we can write in terms of the depth of cut, feed, and the shear strength of the material, right? And here this F is the form factor. Form factor again depends on the uh, tool geometry as well as the material of the tool and workpiece. So apparently the increase in both the feed and feed and cutting speed increases the heat generation proportionately. Now it is seen from the equation that if you increase the feed as well as the cutting speed together, then what will happen, there will be an increase in the heat generation. However, just I told you a few minutes back that in case you're increasing the cutting speed, the cutting temperature will increase. However, if you increase the feed, there will be a reduce in the cutting temperature. However, see in this equation, if you see that both are directly proportional to each other, right? So like in case you're increasing the cutting temperature, cutting velocity, so what exactly happens is faster rubbing action takes place, right? However, in that case the cutting forces are reduced. Okay, but in that case what exactly happens, the heat generation also takes, like heat generation takes place due to this uh, form factor. Okay, so there are few things which you have to consider. You have to consider the entire equation, and depending on the values, we'll be able to select the optimum values of the cutting speed, feed for a certain value of the material removal rate. So you cannot use the maximum value possible for feed and cutting speed, right? So you have to make sure you remember this relation. Okay, so everything here does not, it means as it is shown in the equation, that it is directly proportional to all the factors. However, some of the factors can be like, if you increase the cutting velocity, as it says that the cutting forces are reduced, definitely, as we have discussed previously as well. However, in that case, if the forces are reduced, power consumption will be reduced. So power consumption again is directly proportional to the cutting temperature. So there are many factors that come into picture. You cannot just uh, draw a straight means conclusion that yes, these are the directly proportional factors which will generate the cutting temperature. So there are many things which you have to consider. You have to perform some experiments to check what exactly is happening. And definitely this equation is a very important equation, and you will get direct relations from with the cutting speed and the feed for a certain value of the material removal rate. Now next is the control of the cutting temperature by application of the cutting fluid. So if cutting fluid is applied directly, what there are normally three applications or three functions of the cutting fluid. First is it reduces the cutting temperature. Second is it reduces the friction, or it acts as a lubricant at the cutting zone. And the third is it also takes away the uh, chips along with the flow of the cutting fluid. So these are the three uh, uh, functions of the cutting fluid. So indirectly, if you say that uh, the cutting fluid reduces the friction, that again is related to the cutting temperature, because if you reduce the friction, cutting temperature is controlled. If the chips are removed, again it if chip breaker is not employed, and in few cases, like for brittle materials, what exactly happens, some uh, chips which are discontinuous in nature that are formed. So discontinuous chips can be taken away along with the cutting fluid, right? So purpose of application of the cutting fluid in case of machining and grinding, why we use it, that is cooling the job and the tool to reduce the detrimental effects of the cutting temperature on the job and the tool, lubrication at the chip tool interface and the tool flanks to reduce the cutting forces and the friction, thus amount of heat generation, cleaning the machining zone by washing the chip away, right? And particles or debris, which is if present, spoils the finished surface and accelerates the damage of the cutting edges. And finally, the protection of the nascent finished surface. So there is a finished surface which is just being created, that is, which was lying beneath, and remove material has been removed from that workpiece. So the nascent, newly born finished surface, you can say, has is now in front. So protection of that is very important. From protection from what? Protection from getting it oxidized. So a film of cutting fluid sticks to that machine surface, and it does not get contaminated with the gases in the atmosphere. And definitely there is less reaction that takes place, do not get contaminated. Okay. So yes, I see Niladri has raised a hand. So I have just 10 minutes time. I'll quickly finish. In the next lecture, I'll definitely talk to you regarding that. Okay, I don't have much time now. Kindly bear with me. Again, you can click on the same link and then we'll uh, talk regarding the question answer. Okay. Now, however, the main aim of application of the cutting fluid is to improve the machinability through reduction of cutting forces and temperature, improvement by surface integrity, and enhancement of tool life. Next is to enable the essential properties of cutting fluid are cooling properties, or the high specific heat is required. Thermal conductivity of the material is or of the cutting fluid is very important, and film coefficient of heat transfer for heat transfer is also very important. Okay. Next is spreading and wetting ability. These things are very important for the cooling aspects. For lubrication aspects, we need high lubricity without gumming and foaming, wetting and spreading, high film boiling point. So the film should not boil at a very lower temperature, friction reduction at extreme pressure and temperature, chemical stability, non-corrosive to materials, and like this is the less volatile and high flash point. Okay, high resistance to bacterial growth, it should not be reactive, not be toxic in nature, and it should be available at a very low cost. Okay, principles of cutting fluid action. Now you can see that the chip tool contact zone is usually comprised of two parts. One is the plastic or bulk contact zone, and another is the elastic contact zone, right? So here we can see that the plastic contact zone and the elastic contact zone, that is the total contact zone, and the cutting fluid moves in here. So there is a thin layer of low shear strength, and the cutting fluid moves in here to reduce the friction as well as to reduce the cutting temperature. So the cutting fluid cannot penetrate or reach the plastic contact zone here. As you can see, it remains in the elastic contact zone. It cannot penetrate into the plastic contact zone because this plastic contact zone of the chip is in contact with the rake surface of the tool. Okay, but there is a capillary action due to which it reaches the elastic contact zone. So with the increase in the cutting velocity, the fraction of the plastic contact zone gradually increases and covers the almost the entire chip tool contact length. Therefore, in case of high speed machining, the cutting fluid becomes unable to lubricate and cool the tool and the job only for by bulk external cooling. Like bulk external cooling means, suppose you're flooding it, flooding the coolant on the machining zone, or you have dipped the entire setup into the flood into the coolant. So these things may not take place. So the chemicals like chloride, phosphate, or sulfide present in the cutting fluid chemically reacts with the work material at the chip under the surface, chip under the surface and high pressure and temperature, and forms a thin layer of the reaction product. Low shear strength of that reaction layer helps in reducing the friction. Now, these are important factors, like extreme pressure additive is like for cutting fluid or lubricating. Like suppose we are in, as I also told you that solid lubricants are also available. However, we can also use some mineral oil and some soluble oil for as lubricants. Okay, so some for extreme pressure, chloride, phosphate, or sulfide type extremely pressure additive can be used. Okay, and like types of cutting fluid, we'll quickly go through this. That is, air blast and compressed air can be used as a cutting fluid. And this air blast and it is not for the lubrication purpose, however, only for cooling and cleaning purpose. Water can be used because it has good wetting and spreading properties, and also water has a very good specific heat capacity, so it is considered as a best coolant. And we can also, like in many cases, we can use mix water with some lubricating material, and also because of the high specific heat. So soluble oil water acts as a base coolant, but it does not lubricate. So lubricating factor in case of the chip tool contact is not there in for by or not provided by water. So soluble oil, some water soluble oil can be added with water, and that oil acts as a lubricant, and water in it acts as the coolant, as well as the cleaning part is taken care of. So some kind of milk like white emulsion soluble oil, which can be used in some certain ratio. Okay, Now, cutting oils are generally compound of mineral oil to which are added desired type and amount of vegetable, animal, and marine oils for improving spreading, wetting, and lubricating properties. As and when, like some means additive is added also makes to reduce the friction. Okay, and built up edges are normally, we have discussed that built up edges are formed due to adhesion of the material. The chemical fluids are added or used, uh, um, which are water based, like some organic or inorganic materials are dissolved into water to enable desired cutting fluid action. Like we can have high cooling, anti rusting, wetting, but less lubricating, because in case of chemically inactive type of chemical fluids. However, if we are considering some active, chemically active, that means they have tendency of getting or some kind of reaction, then moderate cooling and lubricating. Chemically active can only be used for surface type. Okay, we cannot get into the subsurface, or we cannot consider it to be entering the through the capillaries. Okay, so the solid or semi-solid lubricant like paste, waxes, soaps, graphite, uh, molybdisulfide may also often be used, either applied directly to the workpiece or as an impregnated in the tool to reduce the friction. Like you can put it inside the tool, you can make a slot inside the tool, and as the machining will take place, that will also get wear off, and that material will act as a uh, lubricant. Cryogenic cutting fluid, liquid nitrogen, liquid carbon dioxide, not oxygen. I just told oxygen before, but not oxygen. Liquid carbon dioxide can be used. Liquid nitrogen. These are cryogenic and definitely without creating any kind of environmental pollution or health hazard. It provides effective cooling. Okay. Now, selection of the cutting fluid depending on the gray cast iron, steel. We have different types of cutting fluid that are available. Different process in which the cutting fluid can be applied. So, cast iron, we told it has a self-lubricating property. It has carbon in the form of graphite. So we do not use any kind of extra lubricant for cast iron. However, air blast can be used for flushing and cooling the flushing of chips and cooling. And soluble oil for cooling and flushing chips can be used. However, lubricating properties, it has its own lubricating properties. For high speed steel, we can have some uh, neat oil. Okay, some we can also have, if carbide tool is employed. Okay, so we can also have some kind of oil for it. Next, aluminum oil. Aluminum and its alloys, they are copper. Depending on all of these, you can uh, see there are different types of oils which are applied. Now, there are methods of application which I'll come into the next lecture. We don't have time much. Thank you very much for attending this lecture. Please click on the same link so that we can continue with the lecture. Thank you very much. I'll end the lecture here.